wonderful symposium. So my talk is named Massive Effects of Saliency on Information Processing in Visual Working Memory. That's the work that I've been doing with my supervisor for the past year in Munich. So what is visual working memory? So working memory as a whole is the mental workspace that we share and use, and it is known to be of limited capacity. In visual working memory, we mainly use two experimental tasks. The first is the change detection task. So it goes like this. You see an array of items, and you have to say whether an item changed before and after the delay. And we also have the continuous report task, where you have to remember the feature of an item. So here, it would be this white square, and it was green, I think. And saliency. Saliency is mostly that, this black sheep in the midst of a white sheep flock. It stands out. Here on the right panel, there's no salient bars, but if one bar suddenly becomes red, it becomes salient. So technically, it's determined by local feature contrast. This is well examined in the visual search literature, but not really in the visual working memory literature. So here we try to close this gap. So how do these two interact? Basic working memory studies, they focus on a few isolated items, which make them all salient because they have no background, no surroundings except the background. So if it's a colored square on a dark background, it is by essence popping out. But in more complex scenes, we don't really know what is a salient item. And how do we encode all of this messy couch? We argue that the saliency of each item might be the determinant of how much resource is allocated to them. So for instance, one could say that this red shirt is salient. And if we were asked to remember this color later, it would be better remembered than this white striped shirt. So for this, we designed 5 experiments, which I'm going to talk to you about. And the first examines how does saliency influence visual working memory performance, with the hypothesis that more salient targets are recalled more accurately. So this is a quite simple design. We have this dense array of bars, 36, and on the middle ring, you can see that there are 3 bars that are tilted. One is tilted 45 degree, one is 28 degree tilted, and one is 12 degree. And that means that the most tilted is the most salient, and the least tilted is the least salient. So we expect that the performance for remembering the 45 degree bar will be better. We use the continuous recall task, and it's important to note that they all have the same relevance. It's not beneficial to encode the 45 degree because it's going to be asked as often as the 12 degree one. So here the participant would have to respond something along the lines of orange. So a trial goes like this. It's a simple change detection task. And so the result is as such. We find an effect of saliency for visual working memory performance. Here we have the recall error on the y-axis measured in average absolute angular distance. So we see here that there's an average of 60 degrees on the color wheel of distance between the target color and what the participant responded for the 12 degree bars. And it goes down to 30 degrees, more or less, for the most tilted. So saliency does improve visual working memory performance. But now we have a second question. What happens when there's not one target that is more salient than the others, when they share the same saliency? Well, we assume that resources should be distributed more evenly. And to test this out, we have the same displays, more or less the same displays as before. And in this experiment, this second experiment, we have 2 types of display. The mixed displays are the same that is in the first experiment. So 3 tilted bars are different tilts. And then the same displays where bars share the same tilt. So this is the same display with 45 degree bars. We also have them for 28 and 12 degree. And what we do find is that first, the mixed results replicated experiment 1. So it's expected because it's the same design, but that's nice. So you see here that there is a difference between the 45 degree, the 12 degree, sorry, the 28 and the 45. The axis shifted, sorry. And for the same displays, so when all targets share the same tilt, there is also an effect, although it is smaller because resources are distributed more evenly. And that also shows because performance increases for 12-degree targets in the same displays. It goes from pretty bad to quite accurate qualitatively, and it also decreases for 45-degree targets in the same displays. So that means that each 45-degree target gets less of the pie, basically of the resource pie, and each 12-degree gets more of the same pie. And then we have a third experiment. Can small eccentricity variation that are typically in visual working memory tasks, because we jitter stimuli and whatever, can they influence also visual working memory performance? And here we set out to test that less eccentric targets would be more salient and then remembered more precisely. So we have 3 squares on this display, so very simple display with different eccentricities, 2 degrees, 4 degrees, and 6 degrees. The circles are for your eyes only, the participants did not have them. And we do find, again, that more eccentric squares, so less salient squares, are recalled less precisely. However, this effect is much weaker than the effect observed in experiment 1 and 2. So what can we say about that? More salient items receive more resources than salient items, than less salient items. That's the result of experiment 1. Salient items receive more resources if presented among less salient items. That's the result of experiment 2. And then in traditional displays, small variation of saliency can influence performance. Okay, so that's the mid-summary about saliency. But then we do know that it influences visual working memory. So how can we modulate this effect? We first tried to modulate this effect with encoding time. So by increasing the encoding time, we expected that performance would increase for all targets, but especially for less salient targets. So we use, again, the same displays as before. However, here we have encoding times that range from 14 milliseconds to 2 seconds, 350 milliseconds being the encoding time that we used in previous experiments. So 14 milliseconds was basically 2 frames on a monitor. That's really short. 2 seconds is way longer than usual studies. So the result is that for all tilts, performance improves with encoding time. And also, interestingly, at 14 milliseconds, the most salient target, the 45-degree one, the squares, is already encoded very well. It's actually encoded better than all the 12-degree targets, except the one shown for 2 seconds. So really the benefit of saliency is already here, and it's hard to override. And even more so that at 2 seconds of encoding time, it is still present when we compare the 45-degree bars with the 12-degree ones. So time is not enough. I mean, at least 2 seconds is not enough to erase this effect of saliency. So the last experiment is, can relevance counteract the effect of saliency? Because if the time alone won't do it, maybe changing the probability will. So we use 3 encoding times. Again, the 350 milliseconds, the standard one that we rely on for comparison with all our experiments, 2 seconds and 3 seconds. We ran a small pilot and we determined that 2 seconds was not enough, most likely to fully override. So we also increased to 3 seconds. So we increased relevance of less salient targets. And how did we do that? We just probed them more often. So on half of the trials, the least salient target was actually the target that participants had to recall. On 2/6 of the trial, it was the middle salient, and on the remaining 1/6 as well, it was the most salient, the 45-degree. And it's important to note that participants were aware of this distribution. So they knew that it was beneficial to encode the 12-degree more precisely for improving their task performance. And we do find again that at 350 milliseconds, there is a saliency effect, and it's not different from previous experiments. So, okay, that's expected because 350 milliseconds is not really a long time to develop top-down control. But we do find, finally, as expected, that there is no difference between the different tilts and the different saliencies at 2 seconds. And at 3 seconds, there is a minor difference between this 12-degree and this 45-degree bar, but in favor of the least salient. So from 3 seconds, it could be that top-down control can really override saliency. This is P.04 with Bayesian evidence not holding up, so maybe we need more time, or maybe it's not strong enough of a manipulation, but it's not a really reliable result, I would say. So in summary, the effect of saliency does decrease over time, and relevance can counteract saliency in the right conditions. So the take-home message would be, saliency is an important factor influencing visual working memory performance. It is hard to override, and it should also be controlled more often, or controlled to begin with, in most visual working memory experiments. Thank you.
Thank you very much. So we have a question from Nelson Cohen, who I hope will be unmuted. So I'll start reading until we.
Am I unmuted now?
You are.
Oh, okay. Yeah, nice talk. I just wondered, you would predict the same results if the background were at some other angle, and I just wondered, I imagine, and I wondered whether we can tell whether it's saliency from the background, since it was the prototypical vertical that was chosen for the background. You know, even if there were no background, could there be a difference just based on the departure from vertical or horizontal? And, you know, so maybe you need to do more with a different angle for the background.
Yeah, that's something that I've been thinking about, although we did not start to test it yet. But I think this effect of saliency could be found no matter the background, at long as we have salient targets. I mean, the eccentricity manipulation showed that small variations could potentially influence also, and there's no vertical background, or they're just salient from fixation, basically, and from the wide range of positions that they can take. But I would say that we can find some differences, maybe not as huge as the one that we find with vertical background, but I'm pretty sure that we could. But that's something that we would need to test, obviously.
Thanks.
Okay, one more question for Martin from Ben. And Ben, while you're asking your question, the Puppet Masters will bring everybody back, and then we'll open up for general Q&A. Ben, are you there for your question? I'll read it. It says, I really like the systematic exploration through all these experiments. I have 3 questions. Well, I'm only going to ask one of your questions, Ben. Can the eccentricity effect be explained by distribution of cones on the retina?
That's something that we've thought about, and that's also one of the comments that a reviewer told us for our paper. And it shouldn't, at least not for this eccentricity, because we would need to have far bigger eccentricities for it to drop dramatically, and to have this really less precise memory feature. And also, fixation was not enforced on the fixation dot, it was just asked of the participant. So they could also in 315 seconds just do saccades. So I guess that no, it shouldn't be explained by the distribution of cone on the retina.
Ben, it looks like you're there. Do you have a follow-up? No, okay. Well, let's transition then to our open Q&A.